very nice presentation. I would like first of all to thank the other authors of this work, Professor Doitrand, Aurelien from the University of Lyon, Professor Cornetti from Polytechnic of Torino, which is the same university of mine, and Professor Estevez from the University of Grenoble. I want to thank also Professor Leguillon for his very nice presentation this morning, which helped me to skip some introduction. So I basically decided to cut some slides, and I decided to start, as in Italy we say, in fourth gear, so in a transient way, let me say. So this is the finite fracture mechanics criterion, which is based on two conditions. The former one is a stress requirement, and the second one is the energy balance. Of course, the stress requirement can be put in an average form, as basically it has been done here, or by involving the function itself, as proposed by Dominique in its original version. So we have two basically conditions. We have the two material properties, the tensile strength sigma u and the fracture energy Gc, and L here is the crack advance. So the system is a system of two inequalities. In two unknowns, the critical crack advance, which, be careful, is not a simple material constant, but it is a structural parameter, and this allows to overcome some drawbacks related to the theory of critical distance and the failure stress, which is implicitly embedded in the stress field and the energy release rate function. So the first goal of my topic will be extend this problem, which was proposed under mode 1 loading condition to mixed mode loading condition. And of course, in this case, the problem is much more complex, since we have an additional norm represented by the crack propagation angle. And finally, I will speak about tensile square holes. So for tensile square holes, of course, the notch amplitude is equal to 90 degrees. And it's very interesting because if you have a square hole under tensile loading, basically, depending on the size of the hole, we can face basically mixed mode loading conditions. So for very small hole size, the crack deviates from the notch bisector, and mixed mode loading conditions are basically faced. And we carry out with Aurelien some experimental tests of PMMA, and I will show you some results. So let us start. So a brief basically outline on what concerns FFM studies, at least to what is my knowledge. The point of, that's very clear. Anyway. The former studies is due to Doitrand in 2006, where they carry out some experiments on PMMA specimen and the three-point bending loading conditions. So the notch amplitude was fixed to 45 degrees. And as you can see here, as far as we move away from the symmetric configuration, which means in the scientific language, as far as the mode mixity increases, the crack starts to propagate, and the crack propagation angle increases as the mode mixity increases. So very, simple fundamentals concepts. Then in a subsequent work, other experiments were carried out on macro basically samples and the four-point bending. And the effect of the notch root radius was also taken into account. And finally, basically, all the previous experiments and other experimental data were basically summarized in this latest work. And so this is a sort of outline on finite fracture mechanics studies. So let's start from the stress field and from the stress requirement. So in the neighborhood of the notch tip, the asymptotic stress field can be put in the following form. So it can be expressed as a function of the notch stress intensity factors, or generalized stress intensity factors, related to mode 1 and mode 2 respectively. Here Fij are some angular shape functions which are known analytically. And lambda 1 and lambda 2 are the classical Williams eigenvalues, which depends on the notch amplitude. And as you can see here, when omega, the notch amplitude, varies from 0 degrees, which is the crack case, to 180 degrees, which means plane specimen. Lambda 1, of course, grows from 0.5 to 1, very smoothly in the region comprised between 0 and 90 degrees. While, on the other hand, lambda 2 increases very quickly. And what is interesting is that starting from, for a notch amplitude equal to 102.6 degrees, basically, it takes the unit value. So for higher notch amplitude, the stress field is no more singular and pure mode 2 loading conditions. And the analysis, our analysis will be referred to notch amplitudes comprised between 0 and 100 degrees. Now, So if we wanted to implement the fine fracture mechanics requirement, we have the stress field, the asymptotic stress field. We insert it into the average version of a fine fracture mechanics, and we get this simple analytical, this simple expression, where here f bar are the angular shape function normalized with respect to some functions, to some expressions of Williams eigenvalue. If we implement the original version of fine fracture mechanics proposed by Dominique, here basically the relationship is the same, but for these lambda 1 and lambda 2 at the denominators. Now, the problem, on the other hand, for what concerns the energy balance is much more complex. Of course, we are able to express the energy release rate in terms of the stress intensity factors related to a crack of length t stemming from the notch tip, and we are able to express the fracture energy as a function of the material fracture toughness. And again, if we suppose to work in the area dominated by the notch stress intensity factors by means of dimensional analysis, we are able to write, to express the stress intensity factors related to a small crack in this way. So this is by means of Buckingham theorems. And what is interesting is that these two expressions encompass the case of course, of mode 1 loading condition, and the mode 1 loading condition, the crack propagates along the notch bisector, and only this term survives, of course. On the other hand, if we have a crack, and this is interesting because, of course, if we have a crack, both lambda 1 and lambda 2 are equal to 0.5, and so the dependence on C disappears. So the criterion reverts basically to the classical Gmax criterion, and we get these simple analytical basically expressions proposed by Mellin in 1994. And so these are, of course, the stress intensity factor related to the daughter cracks, and these are, in this case, the stress intensity factors related to the mother crack or parent crack. I don't know what to say in this case. Anyway, so we have these two expressions. We substituted them into the energy balance, and simple analytical manipulations basically yield to this quadratic form in the notch stress intensity factors. Of course, here mu ij bar are the previous shape functions normalized again with some expression of Williams eigenvalue, and they can be evaluated by means of a numerical analysis as done by Zohar through a path-independent integral, or by means of some semi-analytical basically relationship proposed in the literature. And you can see here that the matching between these two approaches is quite good for a fixed notch amplitude equal to 30 degrees. So now, we have the stress requirement, and we know how to deal with it. We have the energy balance, and we know how basically we can basically solve the problem related to energy. And so now, the system of two inequalities, since the geometry is supposed to be positive, can be expressed as a system of two basically equations. And again, simple analytical manipulations lead to these two expressions. So in the former one, we have the mode 1 notch stress intensity factor as a function of delta xi and psi. And in the second one, we have an implicit equation in delta. So, of course, you can ask me what is delta. And you are right, delta is the dimensionless crack advance with respect basically to Irwin's length, which is defined in this way. Of course, the second question, what is psi? And psi basically is the key parameter for under mixed mode loading condition, is known as mode mixity, or better, mode mixity angle. Is defined in this way. So, of course, psi is equal to 0 under pure mode 1 loading condition, and is equal to 90 degrees under mode 2 loading condition. And what is interesting is that the mode mixity depends on the material properties through LCH, apart from mode 1 loading condition, mode 2 loading condition, and except from for the cracked case, because if we have a crack, lambda 1 and lambda 2 are both equal to 0.5, and so the dependence on the LCH disappears. Okay? So, this is the problem in fine fracture mechanics, basically under mixed mode loading conditions. So the problem can be faced in this way. For a given mode mixity, we have to find the couple delta C and theta C. Delta T is the critical crack advance, theta C is the critical crack propagation angle, which minimizes the failure load under the constraint provided by the second equation. So we can solve it by means of, for instance, Lagrange multipliers. And I will show you some results. So first of all, I will show you basically the extreme cases. Of course, under full mode 1 loading condition, the situation is quite simple. The notch, the crack propagates along the notch bisector. So this is how the previous basically expression reverts. So it's very simple, and we are able to express the notch fracture toughness in this way. That's what these results dates back to 2008, where Xc basically can be expressed by means of this relationship. And according to our definition of the stress fields, basically the notch fracture toughness lies between a fracture toughness for the crack case and a tensile strength on the other end for the plane specimen. This for mode 1. The problem for mode 2 is a little more complex, but more simple than mixed mode loading conditions. So this is the fine fracture mechanics system. Of course, we are able to write it in this way. So now we have to maximize the denominator in order to find the critical crack propagation angle, which is a function of the notch amplitude. So to each notch amplitude corresponds basically a crack propagation angle. And so, for instance, if we have a crack case, so if we have a crack under full mode 2 loading condition, we get this value, which coincides with the well-known value provided by the Gmax criterion. On the other hand, for 102.6, which is the limit, because otherwise, besides the lambda 2 basically is greater than 1, according to finite fracture mechanics, the crack propagates along the notch flanks. And once the crack propagation angle is known, of course we must substitute it into the previous equation, and we get the mode 2 notch fracture toughness, which can be put in a form similar to the previous one for pure mode 1 loading conditions. Okay. So what happens under these mode loading conditions? Of course, that now, well, the numbers are very small. This is made on purpose because you cannot check the validity of them. But now I'm talking to you. Of course, you can find the tables in the reference paper. Anyway, the screen is not so high. So this is just to tell you that we are able to get the critical value of the normalized mode 1 notch stress intensity factor. Once omega, the notch amplitude is fixed, we fix psi, the mode mixity, and we are able to find the different ratios. For instance, for 90 degrees, for psi equal to 0, which means mode 1, we get the unit value, and then of course it decreases up to 0 under full mode 2 loading conditions. Then, starting from this, we are able to put the mode mixity definition to get the K2FB, so the critical value of mode 2, and we are able to do the same thing for the crack deflection angle. So once omega is fixed, we fix psi, the mode mixity, and we are able to estimate the crack propagation angle. Now, more clear. So let us fix now the angle to 90 degrees. So here we have plotted the safety curve, so the critical couples K1FB, K2FB. And so what is interesting, again, this is the definition of the mode mixity. If the loadings are increased in a proportional way, this ratio, K2B over K1B, does not depend on the loading. So we can think that the loading, basically path, is a straight line starting from the origin. And then, of course, for omega equal to 90 degrees, also LCH plays a role. So this means what? This means that for higher LCH, which means for less brittle materials, point A migrates towards point C, which means towards mode 2 failures. On the other hand, for more brittle materials, point A migrates towards point B, which means mode 1 failure. And of course, the effect of material brittleness is higher for larger notch opening angle omega, and the effect disappears, of course, if the notch reverts to a crack. Finally, the last consideration is that for psi less than 5 degrees, so if we are here for engineering purposes, we can neglect the mode 2 contribution, at least for what concerns the failure stress. Now, and of course we can do the same thing for what concerns the crack initiation angle. So this is the mode mixity. Once we fix the mode mixity, we get the critical values of theta. And of course, this is the situation for less brittle materials, and this is the situation, on the other hand, for more brittle materials. Here, basically, I wrote that for what concerns the crack deflection, the mode 2 contribution cannot be neglected. Of course, if we are here and if we move far from here, we get a value different from 0. So there is a crack initiation angle different from 0 degrees. Now, let us speak about square holes. So now, this is the geometry. We have a square hole in an infinite plate. Of course, here the notch amplitude is equal to 90 degrees. And the plate is put under tensile loading conditions. So this is the notch bisector. And of course, the geometry is double symmetric. So from a theoretical point of view, 4 cracks are supposed to initiate simultaneously from the notch tip. And we evaluated, for what concerns the geometry, the notch stress intensity factor related to mode 1 and mode 2. And then basically you can substitute them into the expression of the mode mixity, and we are able to express the mode mixity as a function of the dimensionless notch depth, so as a function of the size of the hole. So as you can see here, the mode mixity increases as the size of the hole decreases. Of course, be careful that the mode mixity in this graphic ranges from, well, this is not 0 degrees, but quite 0 degrees, to nearly 50 degrees, let me say, but covering, I don't see very well, more or less 6 orders of magnitude. Okay, so be careful of this. And here is the situation for what concerns the failure stress. Again, here 6 orders of magnitudes are covered. And you can see that if we consider basically very small hole size, the situation deviates from mode 1 loading condition. Mode 1 loading condition means that the crack propagates along the notch bisector. In this case, of course, the crack deflection cannot be neglected, and here we assume this 2.5 as the limit of our asymptotic analysis. And this is why we don't have basically black dots in this region. And then, so, in order to try to catch this behavior experimentally, we carried out some experiment on extruded PMMA. And, well, first of all, we needed to characterize the material properties. As I told you in the first slide, the approach, fine fracture mechanics approach depends on 2 material properties, K1C and sigma U. And we decided, for what concerns this test, to characterize the material in this way. So we perform basically experiments on circular holes, trying to catch the size effects. And you can see here that the width to diameter ratio of the circular holes was greater than 8 in order to reproduce an infinite geometry. So here for d equal to 0, it means plane specimen, we got a value. Here we got a value, of course, depending on the notch concentration factor, 3, so it's 1/3. And in the value here in the middle, of course, the behavior, the theoretical behavior and the experimental one is governed by the material fracture toughness. So this value was obtained experimentally. On the other hand, the value of the material fracture toughness was fitted on fine fracture mechanics conditions related to circular holes. And from these 2 values, the characteristic length was set equal to 0.2 millimeters, which is basically quite small. Now, once we know the material properties, basically, we decided, of course, it was the purpose of our experiments, to carry out the experiment on square holes. So the strain rate was very low. And you can see here different dimensions, so we consider different, basically, 10 different geometries. Unfortunately, but this is the problem of size effects, we were not able to reproduce an infinite geometry as it was the original, basically, approach. So as you can see here, the W to all side ratio ranges from 3 up to 9, I think, for what concerns this geometry. And so this was the problem, but anyway, it's a common problem if we want to catch size effect. So this is the crack propagation angle, and you can see here basically the value of theta c, which was measured. And of course, we cannot.
Time is over.
3 more minutes. 3 more minutes, and then I start to run. Okay, fine fracture mechanics was implemented by a full finite element analysis, an asymptotic matching approach in order, of course, our previous approach was basically proposed for an infinite geometry. This is not the case. So we had to evaluate again the notch stress intensity factor. I don't want to speak about them because Rafael is going to speak about them after lunch, and I think he's going to speak about them much better than me. And so from a theoretical point of view, going back to the table that you didn't see because the numbers were very small, the mode mixity varies from 16 degrees to 31 degrees, so the range was not so wide, and theta C varies from 26 degrees to 38 degrees. And I want to show you some results. This is basically the failure stress as a function of the all side. So look at here, the comparison is between the finite element analysis results and the asymptotic approach. And you can see here that the predictions are in good agreement. And you can see that the general trend related to experimental result is similar. Generally, basically, theoretical predictions overestimate the experimental value, but the discrepancy is not so high. Those were less than 20%. I think this was the worst case. On the other hand, look at here the crack propagation angle. These are predictions according to the average finite fracture mechanics and its original version. And you can see here that more or less we are in the range, but we had a great scatter for what concerns certain all side. I cannot say that the matching is excellent, but more or less the trend is the correct one, and the theta C decreases basically as the all side increases. So time is quite over, and as last conclusion, at least for what concerns this last part, basically we carried out experiments on PMMA. Of course, we consider our analysis refers to sharp V notches, but of course the effect of the radius can be taken into account, even if it was basically proved that it affects more the failure stress rather than the crack propagation angle. And finally, this does not concern square holes. It's one thing that I have in my mind that it would be interesting to investigate what happens for notch amplitudes greater than 102.6 degrees. Why? Because in that case, of course, the mode 2 contribution becomes non-singular. Okay? So, of course, our asymptotic approach is not able to work anymore. And this is one point. And the other point is what happens for notch amplitudes greater than this value under poor mode 2 loading conditions, because of course the stress thing is no more singular, and according at least to what I presented, fracture should never take place. And that's the end of my talk. Thank you very much.
We have time for one short question.
Yeah,
short answer.
You had a plate with a circular hole to get the material parameters, the strength and the K1C.
Yeah.
Where did you get the K2C from for the simulations of the square hole?
No, the model is just based on K1C. So in the
Yeah, but the mode mixity will depend on the two, isn't it? So how do you?
the mode mix, it depends on the notch. Maybe I can show you. The mode mix, it depends on the value of. Here maybe. The notch fracture, basically the notch stress intensity factor.
Mm-hmm.
Okay. So not the.
So you don't need K2C in the analysis
Well,
at all.
of course,
That's
everything. Yeah, this is right, of course.
Yeah.
But because it's the previous slide, sorry. We have time?
No.
No, okay.
Okay, we can talk
We can
later.
discuss
Yeah.
afterwards. And then